everyone to Astrobiology Journal Club. Welcome everyone who's online joining us for our second installment of the Origins Institute Journal Club for this term. Today we have Nick Randazzo, who's a grad student here, PhD student here at McMaster in the Department of Geography and Earth Sciences, yes. And he'll be talking today about a recent paper that was published in Astrobiology by Dr. Nathalie Cabrol on the coevolution of life and environment on Mars. So, take it away.
All right. Well, thank you, Ben, for that introduction. I'm just going to stand here so the camera. Good afternoon, everyone who's here and everyone who's on SAGANet. So, as Ben said, my name is Nick Randazzo, PhD candidate in the School of Geography and Earth Sciences. And today we'll be talking to you about the coevolution of life and the environment on Mars, an ecosystem perspective on the robotic exploration of biosignatures. So, a few objectives of this talk today are to discuss the concept of coevolution and how it may be the key to the search for life beyond Earth. We're also going to illustrate how existing data provides a foundational framework where coevolution models can be explored. And we're going to describe hypothetical locations for life on Mars. And finally, demonstrate the importance of starting to think of early Mars as a biosphere and rigorously integrating an ecosystem approach to landing site selection and exploration. So, by the end of this decade, Mars 2020 and ExoMars will be set out in search of biosignatures on Mars. And landing sites are typically selected because of their physical characteristics, which are consistent with habitability of early life, favorable conditions for biosignature preservation, which could have evolved either locally or elsewhere and then migrated to the site of interest, and finally, what's safe and accessible. You can see on the left here is an image of what Mars 2020 will look like, and on the right we have the European Space Agency's ExoMars, Exobiology Mars, which is actually in two parts. The first part is the orbital tracer, which was sent in 2016, and this is just a landing module that was sent to Mars to just test payload and entry and have you, and this is the actual rover that will be launched in 2020. So, current research regarding Mars relates to the origin of life with terrestrial biology and organic chemistry in mind. And Cabrol argues that this causes some knowledge gaps about the sustainability of habitable conditions because this viewpoint is constrained and we haven't evaluated the ecological potential of Mars to its entirety. So, searching for biosignatures involves a systematic understanding of coevolution, life with the Martian environment, and this is a synthesis of what we have learned so far about Mars's habitability as well as environmental factors that have changed over time. So at this point, when we're thinking about the future of Martian exploration, we can think of Mars in terms of the biosphere, ecosystem, and ecology. Keep these terms in mind, which previously we have unacknowledged. So obviously, it's unknown if Mars ever hosted life, but if it did, the Martian environment and the characteristics that occurred on the surface and subsurface would have had an important or even overreaching role in the evolution of any sort of indigenous species. So we can start to think of these things through a more holistic perspective instead of a discrete set of variables. And this would give us a more systematic, substantiative, and informed approach to where to search in the future. So just a few background concepts we're going to discuss before we really get into the paper. So on Earth, the biological and environmental evolution are inseparable. Evolution of early life took advantage of dispersal pathways, which are intimately connected to the biosphere and interactions with the lithosphere, atmosphere, hydrosphere, what have you, as well as spatial temporal changes. The lens in which we view the evolution of life in the biosphere on Earth can vary depending on the lens in which you view it through. So, for instance, a reductionist view provides some snapshots. So if you were to divide Earth's biological history into three parts, it would be the prokaryotic Archean, the eukaryotic Proterozoic, and finally the Cambrian Earth, so post-Cambrian explosion where larger organisms came into being. And though this is very useful, this provides very little information regarding how each of these three distinct periods are interwoven together. So in the future, we need to start to think about how life adapts, survives, and changes, and integrate multiple scientific fields when looking for life on Mars. So past research on Mars has focused on habitability, and Cabrol argues we should start to think about habitats as well. So just the definition of habitability are the general conditions favorable to life on local or global scale. And this includes things like water, nutrients, energy, what have you. Habitats, on the other hand, are defined by their inhabitants, and this has a focus on microorganisms as well as spatial temporal dynamics. And so far, searching for life on Mars can be seen as equivalent to exploring the Archean record on Earth. So far we've been using orbital data and spatial resolution. We've done a lot of work on the Gusev and Gale craters. This is actually an image of the Gale crater in the lower right-hand corner with Mount Sharp in the middle. And we've also looked at the Meridiani Planum area on Mars. So Mars itself can be divided into three distinct geologic periods: the Noachian, the Hesperian, and the Amazonian. So the Noachian is characterized by heavy bombardment as well as valley network formation. The Hesperian was a period of increasing aridity as well as intense volcanism, outflows, and possible ocean. And the Amazonian has residual flood, volcanic, and glacial activities. And it's during this period that Mars began to resemble the planet that we all know today. So scientific questions that we should formulate when looking at Mars through an ecosystem perspective are: what role did the environment play on the early evolution of Mars? How did unique physical features impact environmental pathways and biological dispersal? And finally, what does a comparison between the timing of life on Earth and environmental models of Mars suggest about ancient habitable environments, habitat development, biological dispersal, biosignature preservation, and detection thresholds? So the earliest indirect evidence for life on Earth that seems to be relatively agreed upon is 3.8 to 3.7 billion years. But there are other research, like Jack Hill's Australia, they found evidence suggesting 4.1 billion years. And the site in Quebec, which we discussed here in the Origins Department just a few weeks ago, suggests 4.28 billion years. And these are a bit uncertain, but the whole concept of life being present at this time is completely plausible. So there's a few explanations for how Earth originally developed, or how organisms developed on Earth. The first one are the warm little ponds. We also have hydrothermal vents and hot springs, volcanic aquifers, etc. And plate tectonics is essential to development on life because it has to do with the habitability trinity, which is essentially just oceans, landmass, and the atmosphere interacting together. Plate tectonics itself is important because it controls rock cycling, continent formation, and destruction of continents. And it also affects mineral systems, the environment, and nutrients. So, geological history of Mars is reasonably complex and interesting. The Pre-Noachian Mars covers the accretion time, as well as the formation of the Martian dichotomy, which we'll get to in a moment. The beginning of the magnetic field loss and changes in the atmosphere. So unfortunately, little record of this period is left. But it is a potentially key period to coevolution on Earth, just based off the research that I referred to just a few slides ago. And potentially the same thing might apply to Mars. Unfortunately, because we don't have a lot of information about this period, we do view it through a low-resolution lens, and therefore a lot of important details are just lost to generalizations. And also, the current data that we do have is not adapted to characterize microbial habitat, but we can use it to help articulate some of the questions that we might have, including the three that I mentioned earlier. So the Martian global dichotomy essentially talks about a sharp contrast between Mars's southern and northern hemisphere. So the northern hemisphere is comprised of mainly lowlands, whereas the southern are highland. It's very mountainous, it's not flat terrain, and both of them are covered in impact craters. During the Pre-Noachian times, there was a theoretical presence of land masses and islands in a primordial ocean. So therefore, if life did exist at this time, it would have had access to subaerial dispersion pathways. There's always the possibility of subsurface and underground circulation as well, which would occur in fractured regolith and crust. The Barberton Greenstone Belt in South Africa could potentially explain the fate of the primordial ocean. So this was originally an oceanic spreading ridge, but there's evidence of impact crater, so potential that the primordial ocean, which formed on Mars, just due to impacts in general, could have caused the boiling and vaporization of the top ocean layer, but still maintain subsurface and underground circulation. So Mars has a scarce geological record of the Pre-Noachian, and we don't know if there was a primordial ocean or not. But let's say hypothetically there wasn't. There was still active volcanism during this time, which could have supported the development of a seafloor aquifer that's heated by magma. Hydrothermal activity was widespread, especially at the equator. And as we've seen on Earth, redox reactions have been sufficient to sustain life, and a similar thing could have happened on Mars during this time period. And we know that the largest reservoir of prokaryotes on Earth actually use redox reactions to survive, and they don't need to be on the surface itself. So dispersal pathways on Mars depend on global fluid circulation, as well as obliquity, which would affect it, and strong cyclic climatic swings, which affect stability of unconfined and shallow aquifers, as well as physicochemical properties such as texture, pore size, nutrients, chemistry, etc. come into play. An alternate environment, like I said before, volcanic aquifers, which there's ample evidence of its existence. We know it's sheltered from subsurface, and it could be analogous to early Earth. And there's also hydrothermal systems created by impact cratering. So these would have lasted for tens of thousands of years. It's also associated with weathering and acidic environments, and serpentinization of basalt and other mafic lithologies, if primordial ocean existed, could have also been a source of heat, as well as hydrogen and methane, which would have been exploited by microorganisms to gain metabolic energy and biomass. So pre-Noachian dispersal pathways, like I said before too, deep crustal aquifers maintained by a geothermal gradient, and active subsurface connected by fluid circulation affected by climatability and stochastic events could have allowed organisms to spread and flourish. The Mars atmosphere and volatile evolution, or the MAVEN space probe, looked at the argon isotopes and found that it appears that early atmospheric loss began around roughly 4.1 billion years ago, just from intense UV radiation and solar winds. This is when the sun was at its T-Tauri stage. And there's also a decline in valley formation and network changes to mineralogy at the time. So during the Noachian period, like I said before, it was heavy bombardment, but this could have allowed for habitat formation, destruction, as well as dispersal, extinction, and biodiversification. And many of these impact sites are associated with volcanic, lacustrine, and hydrothermal activity. Noachian also has a very robust hydrological record. It's possible that microbial migration could have spread through regolith and crust, forming ecotones between different ecosystems. And also the Noachian had a denser atmosphere than what Mars has today, and it's believed that it could have supported actual rainfall, which could have led to weathering of surface rocks and diversity of phyllosilicates being produced that could form under chemical conditions that were conducive to microbial life. But there's a Noachian paradox. So theoretically, life could have occupied diverse, connected, and widespread habitats, and could have migrated through diverse dispersal pathways through water currents and hydrothermal events created by impact ballistics. However, sterilization processes occurred at a global scale during this period. And as I mentioned before, the magnetosphere began to dissipate at this part. We were losing it, and on Mars, there's a 1,000 times biocidal effect from UV radiation than you witness on Earth. But the Curiosity rover had a radiation assessment detector, or RAD. Here's an image of it here in just a brief schematic. And it found relatively constant and negligible radiation. It also found that most of the radiation was coming from galactic cosmic rays, which I'll get to in a moment. And it noted one solar particle event in every 300 sols. The galactic cosmic rays, it's argued that biomolecules are compromised by dose accumulation and not instant exposure. And sterilization depth depends on the minerals that, let's say, is shielding the microorganism. So we believe that there would have been localized environmental shielding from the UV, and this could be caused by a very thin layer, let's even say 1 millimeter of dust or regolith. So here's a brief image that's showing some interaction between extreme environmental parameters over Mars at this time. So the white arrows just show things that are promoted, black arrows are counter, gray is a combination, and the dotted line shows loop cycles. And we see that there are a variety of pathways that could actually lead to UV and temperature protection during this time period. So it's uncertain whether life in general during the Noachian would have had time to produce biomass at a detectable concentration, and therefore further research is needed, and we need to gauge the complexity of Mars even during these early stages. It's a combination of multitude of environmental extremes and variability and how they interplay over time, as well as complex loops and feedback mechanisms which are at play that we need to better understand. One thing we do know, though, is Mars became polyextreme relatively quickly, and this suggests evolution towards polyextremophiles, hyperadaptable communities, and oases created by local factors. Any sort of biological footprint would have depended on where habitat conditions were met, and this could be places like a crack in a rock, an exposed slope exposure, specific mineralogy, etc. And currently have a limited understanding of the effect of polyextremes on microorganisms, and this impairs any exploration of biosignatures. So during the Hesperian period, it was a highly effective time for dispersal, and there's much stronger empirical and theoretical support, though some debate exists, for an ocean or shallow seas in the northern hemisphere, this is the lowlands, and subaerial habitats increasingly unlikely after the Noachian. This again is because of the loss of the magnetosphere, but groundwater circulation from highlands to lowlands are noted, as well as there's a strong potential for deep sea vents and seafloor aquifers. So during the Hesperian, valleys marinaires, which you can see just at the bottom here, and the Tharsis volcanoes, which are on the right, but not that far from the Olympus Mons, they're environments of high energy concentration and dissipation through volcanic and tectonic activity. And hypothetically, during this point, if it was too cold for ocean, there are numerous underground hydrothermal events which could theoretically again support life.
You mentioned that we would have a thick atmosphere possibly at this time.
Thicker than it is today.
Yeah, but nowhere approaching it.
Nowhere approaching like let's say Earth's atmosphere we have there, yeah. But and it would have been increasingly thin throughout the Noachian, and then once you reach the Hesperian, it was more or less gone. So the MAVEN space probe found that Mars was volcanically active during the late Amazonian. So this is the final geologic period that Mars is currently in today. There was catastrophic dispersal repeated through episodic outflow activity in the Tharsis region, which are the 3 volcanoes that I showed you earlier, as well as possibly another area known as Western Elysium. The Amazonian was also hyper-arid and cold. And a succession of episodes in the Northern Highlands was a region, led to possibly the Northern Highlands is a region where biomass could have been abundant, concentrated, and protected under sedimentary deposits. So, because the Amazonian is the final period that we know today, as I mentioned, it has been relatively geologically quiescent for the past 3 billion years, and little surface change has occurred since the end of the Hesperian. But volcanic activity and volcanic ice interactions do still occur, or did still occur during that 3 billion time period with the Amazonian. And the energy in water is still present hundreds of thousands, tens to hundreds of millions of years ago at a depth in the equatorial region. And once again, this enforced the possibility that the Martian biosphere could have been active at least during that time period, until that time period. So the future search for biosignatures, biomass repositories, potential and analogies between Earth and Mars, they're being redefined with each mission. There's no visible signs of biological interference with the surface, at least using our current detection methods. And early subaerial habitats may never have had the opportunity to form or even rebound from environmental change. However, there was always greater habitat stability in the subsurface, and if coevolution did occur on Mars, it may have forced life to shrink its footprint or even retreat into the subsurface. And as we've seen on Earth, there are many organisms which do not rely on surface processes or surface organisms to flourish. Example, biofilms attached to mineral surfaces, which rely on thermodynamic equilibria to survive. Here's a pretty simple diagram. This is actually from Cabrol, just showing the likelihood of microbial habitats, ecotones, and dispersal during the Noachian, Hesperian, and Amazonian period. So you see the surface was highly probable during the Noachian, started declining during the Hesperian, and was essentially nil by the Amazonian. But it's reasonably consistent during the subsurface, and it is definitely consistent in the deep underground throughout all 3 periods. So if life did form in the deep underground, it would have been relatively unaffected by any of the processes that we've observed on the Martian surface so far.
How deep?
How deep? Not sure. Deep was given as a relative term. But yeah, I'm not 100% certain. That would be good to know though.
Nick, I know the answer.
You know the answer? Go for it.
Yeah, when they talk about Martian subsurface, they're talking like 100 meters below the surface. When they say deep underground, that's when you start getting into like deep crustal
So 100
kilometers.
So 100
like
plus,
100,
roughly.
200 meters, which isn't so bad for looking.
Yeah, it's not out of the realm of possibility. So this diagram here just shows primary dispersal pathways and biomass repositories. So the red arrows show, they represent potential primary biological pathways. I labeled some of the areas, and the blue arrows are hypothetical shallow dispersal paths along the coastal marine currents, and the boxes indicate some of these deep biomass repositories. So there's Hellas, there's Arabia Terra, which Arabia Terra can get to in a moment. There's a few others. So Arabia Terra and Valles Marineris are just natural topographic traps for underground water circulation originating from the southern hemisphere. There are also areas of large interaction between the lithosphere, hydrosphere, and energy sources. Currently, we can't detect anything using the means we have so far, but there are some potential interesting research areas, like a mysterious source of methane that was detected just outside of Arabia Terra. Perhaps it's biological, I'm not sure. And temperature, moisture, light, mineralogy, sediment texture, pH, etc. would have differed, or potentially could have differed greatly from the surface compared to the deep ground, deep underground. But we know for sure that most likely would have stayed stable over time. So There are a few records that we might be interested in that are currently within reach, one of which is from minerals extracted from original geological settings by impacts and hydrothermal activity. And this relates to streams, glacial and periglacial processes, landslides, tsunamis. And landing sites evaluated through geological, geochemical, and compositional evidence, which would focus on microbial evidence and interactions, or lack thereof, between past microbial habitats, their occupants, and the environment, is a possible suggestion for where we could go in the future. And we currently lack the orbital data with a adapted spatial scale and spectral resolution to tell us more about it. Ancient habitat sites may not necessarily translate to potential habitats on the surface today, so they could have been habitable back then, but obviously things will change. So we need to identify emission thresholds from the orbit to the ground. There's actually a suggestion of going to a 1 centimeter per pixel imaging, which is beyond the current imaging that are on the rovers, which is 10 to 15 centimeters per pixel. That's the current recommendation. But if we did, this would actually resolve geomorphic features consistent with potential habitat. It's actually kind of similar to my own PhD research of what we're doing in Utah, New Mexico. And there's also orbital spectral resolution, and it's suggested using the CRISM resolution, which was just recently suggested in a recent paper. And that's, so from the orbit, a resolution of approximately 6 meters per pixel. It's also suggested that we integrate a variety of techniques developed in microbial ecology. So there's been some work in the Atacama Desert in Chile, development of an ecological mapping technique adapted to autonomous rovers and predictive maps of habitat potential. So that work is starting to get completed, and develop an ecosystematic view of a region before landing. So in conclusion, searching for biosignatures requires a systematic understanding of coevolution, about habitability and environmental changes. We need to make inferences on hypothetical biological processes based on the data that we have. There are obstacles faced during the Noachian era that are similar to those of Archean Earth. And we need to fully understand the regional and local hydrogeochemistry effects on biological cycles and biogeochemical cycles and biological processes. Finally, ultimately the subsurface was more stable on Mars and would have allowed the development of specialized microbial communities. High spatial and spectral resolution orbiters are also vital for the future of research. Dynamic mapping and the distribution of localized hotspots or potential windows into the subsurface and deep biomass vaults would be key to looking for life in the subsurface and deeper. And this could potentially be a cornerstone for future exploration on Mars. So it's an exciting time in the exploration of Mars. I hope you enjoyed this talk. Thank you very much. Most of the information that I received is based on this Cabrol paper here. Please see the reference page for citations. I also have some more citations that I used. Feel free to contact me and I can provide them upon your request. Thank you.